Hello, everyone. Welcome to Week 14, Data Structures. This is David Ostrowski. In this recording, I'm going to be discussing the greedy technique. And this is also in support of our final programming assignment, which has been posted to the announcements. I'll be adding some more details and additional data sets to be running with the program to demonstrate its usage. I already have an initial data set, but I'm going to post a few more. And I'm going to be adding some more detail. If you have any questions or anything related to that, feel free to contact me. And again, I'm going to have a live session tonight, actually, and that'll be recorded. I'm going to try to have a live session next week as well before the final exam. So we're sticking to the syllabus, and we're going to have the final exam coming up. So use effective time management. If you have any questions or anything, feel free to reach out to me. So here, let me get started on the content here. So greedy technique, okay, and there's a number of ways to implement the greedy strategy. But it's presented initially as a generic technique. You can choose any of the techniques available. You are obviously can build on the graph abstract data structure that you worked with for the last programming assignment, and you're just going to extend it slightly, okay, to implement these strategies. So let's talk about the greedy. Okay, greedy constructs a solution to an optimization problem through the sequence of choices that maintain the following qualities: that they're feasible, locally optimal, and irrevocable. So for some problems, you would yield an optimal solution for every instance. For most, it does not, but can be useful for fast approximations. So a number of applications for greedy strategy. Some of the optimal solutions include change making for normal coin denominations, minimum spanning tree implementation, MST, single source, shortest paths, simple scheduling problems, and Huffman codes. Some approximations include the traveling salesman problem, TSP, knapsack, and other combination optimization problems. And as we start getting to some of these more advanced problems, okay, we're going to be addressing the topic of NP complete just before the completion of the class. So you want to be comfortable and familiar with these problems and how they vary from each other, and also how they fit into similar classifications in accordance with their complexity. Okay. Change making problem. So this is described. They give an unlimited amounts of coin denominations. Okay. You're not limited at all. Okay. Unlike a traditional cash register might be limited, right? So here you're going to give a change for the amount defined as n with the least number of coins. So this can be viewed intuitively as a greedy strategy, right? That you would work, and this is how a cashier, again, given an appropriate supply, is going to work with the highest denomination down to the smallest. Here, if we're just looking at making change from $1, okay, you would be working with, as indicated here, with a quarter, dime, nickel, and then and penny. So here, the greedy solution, this is the optimal for any amount in typical set denominations. It would be not optimal for all coin denominations. So greedy is not optimal for all sets of denominations. Consider 1, 3, and 4. What values of the greedy algorithm fail? Here, if you're going to skip 2, then obviously you would, sure what they're specifically asking for here, but obviously your strategy is going to change if you are limited in the types of denominations that you have, and you would just work from the highest down to the lowest, okay? That being the greedy strategy. So minimum spanning tree MST. So the spanning tree of a connected graph G is a connected acyclic subgraph of G that includes all of G's vertices. Here, a minimum spanning tree of a weighted connected graph G is comprised of a spanning tree G of minimum total weight. So in all these examples, okay, we're dealing with, in this case, a weighted graph. Okay, so here we have the associated weights, and let's move forward with the algorithm. So here you'll start with a tree identified as T1 consisting of 1, this could be any vertex, and grow the tree 1 vertex at a time to produce a minimum spanning tree through a series of expanding subtrees, T1 through N. On each iteration, we construct Ti plus 1 from T of I by adding vertex not in Ti that is closest to those already in T. This would be a greedy step, okay? And you would stop when all the vertices are included. So here's an example. We have the given graph. And we could work that in perhaps a later description. Okay, so next they talk about Prim's algorithm. So this leverages proof by induction that this construction actually yields a minimum spanning tree. Here we use a priority queue for locating the closest fringe vertex. The efficiency for Prims is big O log of n squared for weight, matrix representation of graph, and an array implementation of priority queue. And O m log n for adjacency list representation of a graph with n vertices and m edges, and min heap implementations of priority queue. Now the greedy algorithm is Kruskal, and this is where you sort the edges in a non-decreasing order of lengths and grow the tree 1 edge at a time to produce a minimum span tree through a series of expanding forests. And on each iteration, you add the next edge in the sorted list, unless it would create a cycle. If it would, then otherwise you would skip the edge. And again, we can work these out a little bit later, but just want to introduce some of the basic algorithms here. Kruskal's, so here the algorithm is easier than Prim's, but it's harder to implement. You're checking for cycles. The cycle checking, a cycle is created if an added edge connects the vertices in the same connected component. Shortest paths, Dijkstra algorithm, so single source, shortest paths. Here we have a weighted connected graph. You find the shortest paths from the vertex to each of the other vertices. Here, similar to Prim's, you have a different way of computing the labels on the vertices on the tree. You find the vertex with the smallest sum, where V is a vertex for which the shortest path has already been found on preceding iterations. So here, when you're adding the vertex, you're adding them as a path and not just adding the value. And the consideration now is the length of the shortest path from the source to the next edge that you would represent. So here's an example of Dijkstra, and we're dealing with A, and then this is in light of B, C, D, and E. Okay, so the next available to be considered would be B and D. We wouldn't be able to go from A to C or E. And here you choose B because it's a path of 3. So now you're at the vertex B, and you're only considering the remaining vertices of C, D, and E. So among the considerations, we have the added distance, right? We have B is at 3, and then coming from B to C would be would be 7, and if I go from B to D would be 5. So I would logically choose D, and that would remain the remaining here would give me consideration among C and E. And I would take now I consider both from B and D, and here I would take the path from B, because that would be 7 as opposed to 9, and then you have the final D, 5 plus 4, or that would take me to E. Okay, from the D, so I can either go to C. That would take me to 7. That would be the lowest path. And then from D, E to D, from D to E, from D to E would be the 5 and 4, and that would be the 9. So here I choose a 7, right? And then I have the D of 9, and I get to the final path. Okay, so I have trouble reading the put my glasses here. Okay, so some notes on Dijkstra. Okay, doesn't work for graphs with negative weights. It's applicable both on directed and directed graphs. The efficiency is big O of vertices squared for graphs implemented by the weight matrix, and array implementation for priority queue. It's also big O E log V for graphs represented by the adjacency list, and min-heap implementation priority queue. And you want to make sure that you are not confusing between Dijkstra and the purpose algorithm. Okay, so for some of the coding is assigned of bit strings to alphabet characters. Code words include bit strings assigned for characters of alphabet. 2 types of codes is fixed length. ASCII, a variable length would be, for example, Morse code. Fixed prefix free codes. No code is a prefix of another code word. If the frequencies of the character occurrences are known, then we ask the question, what's the best prefix-free code? Huffman codes is here. Any binary tree with edges labeled with 0s and 1s yields a prefix-free code of characters assigned to its leaves. Here, an optimal binary tree minimizes the expected weighted average length of a code word. It can be constructed as follows. Hoffman's algorithm, you would initialize an n one node tree with alphabet characters and tree weights with their frequencies. Here you repeat the following step n minus 1 times. Here you join two binary trees. Smallest weights into one as left and right subtrees and make its weight equal to the sum of the weights of the two trees, and then mark the edges leading to left and subtrees with zeros and ones respective. Here's an example. We have the characters, ASCII characters, A, B, C, D, we have associated frequencies, we have a code word. We can associate average bits per character for fixed length encoding and establish a compression ratio. So that would all give us a premise for the encoding types of representation. Okay, that could be leveraged here. Let me pull another presentation and kind of take another pass through these algorithms here. So let's make another pass through here. And again, let's look at the greedy principle at a high level. Okay, here we are required to find a feasible solution that either maximizes or minimizes an objective solution. Here, it's easy to define a feasible solution, but not necessarily an optimal solution. The greedy method solves a problem in stages. At each stage, a decision is made considering inputs that are already determined by a selection procedure, which may be based on an optimization measure. And the difference here, right, as opposed to other strategies, is the greedy algorithm always makes the choice that looks best at the given time, right? It optimizes to locally, okay, among all the decisions and potential solutions it's going to take. And this is irrespective of the fact that you could be trapped in a local optimum, okay, and not result in a globally optimal strategy, okay. And this can be like among a number of different solutions, including pathfinding, where the greedy could lead you down a path that would not be optimal at all, and just a lot of short-term gains, but not take you to the complete final objective, right? So one type of application is used in scheduling, and here you have an activity selection problem. So here you would schedule a resource among several competing activities, where S goes through 1 through N is the set of N proposed activities. Here the activities share resource, which can be used by only one activity at a time. Each activity I is designated with a start time and finish time, where the start is less than F. When it's selected, the activity takes place during the time S I of SF. The activities are compatible if S of I is greater than F of J, or S of J is greater than F of I, right? So the activity selection problem, it selects the maximum size set of mutually compatible activities. And here the input activities are in order by increasing finishing times. And here I have the finishing times are sequentially are greater than each other, and they can be sorted in big O and log n time. Here's an algorithm for the greedy activity selector. I have a length and order of increasing finishing times, where A is initialized to 1, so the first job to finish. J is initialized to 1, and I goes from 2 to N. And you do if S, the starting, is greater than or equal to the finish, or S of I is greater than or equal to F. And here you would take the I and union that to A and assign I to J as you increment through. So initially we choose activity 1 as it has the least finish time. Then activities 2 and 3 are compatible as 2 is less than F1 and 3 is less than F1. Here we choose activity 4 where S of 4 is greater than F of 1 and have activity 4 to set A. So then we end up to the set of 1 and 4. Next, activities 5, 6, and 7 are incompatible, and activity 8 is chosen. And that results in activity 1, 4, and 8. Finally, activity 10 is incompatible, and activity 11 is chosen. And the resulting list of activities is 1, 4, 8, and 11. Here, the algorithm can schedule a set of n activities in omega n time. Minimum cost spanning trees. Here you would consider a network of computers connected through a bidirectional link. Here each link is associated with a positive cost, and this is broken down as the cost of sending a message on each link. Here this network can be represented by an undirected graph with positive costs on each edge. In a bidirectional network, we can assume that the cost of sending a message on a link does not depend on the direction. Here, if we suppose we want to broadcast a message to all the computers from an arbitrary computer, the cost of the broadcast is the sum of the costs of links used to forward the message. For minimum cost spanning trees, here you'd find a fixed connected graph, subgraph, containing all the vertices, such as the sum of the costs of the edges in the subgraph is the minimum. Here, the subgraph is a tree, as it does not contain any cycles, and such a tree would be referred to as a spanning tree since it spans the entire graph of G. Here, a given graph can have more than one spanning tree. The minimum cost spanning tree, MCST, is one whose edge weights add up to the least among the spanning trees. So spanning trees could be applied to a local area network. And here we have an equivalent graph that will be generated from that. And the minimum cost trees, as we have identified trees working between the all the different nodes in the network. So here we would obviously disclude the path of 6 and 5. Those are very expensive. And we would identify the simplest paths between any of the associated nodes. So minimum costs, here we're given an undirected connected graph of weight G, comprised of the vertices and edges. Find a spanning tree T of G with the minimum cost. And this relying on the greedy algorithm for finding the minimum spanning tree. It's also called Kruskal. And at each step of the algorithm, make one of several possible choices. And here the greedy strategy makes the choice that is best at the moment. Here's a breakdown of Kruskal. Okay, so here you would have as input an undirected graph, G, V, and E with cost function C on the edges. The output is the minimum cost spanning tree. You initialize them T and VS to 0 for each vertex within the larger set of V. You would add the vertice to the set of vertices. You sort the edges of E on non-decreasing order of weight. And while the set is greater than 1, you choose an edge of the lowest cost and then delete it from the list of edges. The V and W are in different sets, W1, W2, add W1 union with W2, or and you would disclude that from the set of vertices. And here you would union that to the output tree. So with Kruskal, the algorithm contains a collection VS of disjoint sets of vertices. Each set W and VS represents a connected set of vertices, forming a spanning tree. Here, each vertex is in a set by itself in VS, the vertices set, and the edges are chosen from E in order of increasing costs. We consider each edge VW in turn V and W within the set of vertices. If V and W are already in the same set, say W of VS, we discard the edge. If V and W are in distinct sets, W1, W2, meaning V and or W, not in T, then we merge W1 with W2 and add VW to T. Kruskal, okay, here consider the graph. The edges in non-decreasing order. And here we have the edge action sets in the VS spanning tree, T, and then you would perform the associated merge and do the subsequent merges here. Need some glasses to see this appropriately. Okay. And move forward with the additional considerations until you have generated the final minimum cost tree, right? So I'm not going to go through all the transitions, but you can see how it works through the graph and the associated edges. So if you look at the complexity of the output of the algorithm, steps 1 through 4 take the time big O of V. 5 sorts the edges in non-decreasing order, big O E log V time. 6 through 13 takes big O E time. The total time of the algorithm is given by big O E log E prime. Here the edges can be maintained in the heap data structure with the property E edge of the parent less than E of I. And here the properties outside the one used in the heap sort earlier. This is used to sort the data elements in non-decreasing order. You construct a heap of edge weights, the edge with the lowest costs at the root, and during each step of the edge removal, delete the root from the heap and rearrange it. The use of the heap data structure reduces the time taken because at every step we're picking up the minimum or root rather than sorting the edge weights. So if I start from A is logically going to pick between the separate nodes. We have 3 to F, B, and D. It's going to pick D because it has the most weight. From D, I have 5 in consideration and 1, and it's going to pick C. From C, it can pick from 2 to 6. It's going to pick 2 to F. F has the choice between 3 and 2. It's going to pick 2. and then finally from A, it's going to pick 3. So here, we're not only picking from that, so the thing to keep in mind here, right, is so when I take D, for instance, the choice from D, I'm not only considering from D to E, I'm also considering from all the given nodes, right? I'm going to pick the lowest path. So I consider from D to E, A to F, or A to B. So this is 3 and 3, and this is 5. So that's why I pick the 1, because out of the 4, I have four paths to consider from A and D. Here I have all the paths from A, D, and C, right? So I have 3 from A, D has 5. C, we already used the 1, I have the 6 and the 2, so that's what 6 the 2. That's why when we satisfy E, we have the choice 5, and we've already gone from F to A. But from A, we have the path 3, so it's 5 versus 3, and that's going to give us the final graph representation. So another consideration here is the single source shortest paths. Here, Mortis wishes to find the shortest possible route from Perth to Brisbane. Given the map of Australia on which the distance between each path of cities is marked, how can we maintain the shortest route? The single source shortest path, we're given a weighted directed graph with the weights assigned to each graph edge in the graph. The weight of the graph is V1 through K. It's the sum of the weights of the constituent edges. Here, the shortest path from U to V is given by a distance of U to V. I have the minimum of the weight of P if there are one or more paths from U to V. Otherwise, it's set to infinity. Single source, shortest path problem. Here, if I give in the graph G, V to E, find the shortest path from a given vertex. U to V to each vertex, V, and containing the set of V, right? So U is not equal to V for each vertex, V within the set in the directed, weighted directed graph. dV represents the distance from U to V. Initially, dV is equal to 0 and U is equal to V. It's equal to infinity of U of V is not an edge, and dV the weight of the edge UV if UV exists. So again, with Dijkstra at each step of the algorithm, we compute the minimum of distance, okay? And it's not, so this is separated from the last algorithm that we're just working independently from each node. Here we're looking at consideration of the path that's already built up. So if I go down a very expensive path, even if I have a shorter node, it's considered as the total distance. So that's where we talk about distance, and that's considered against the associated weight. Here I have another example, and here we can work through the Dijkstra algorithm, and we have the step, the vertex to be marked, and let's see if we have, so we have U here at step 0, and U can go to and it's directed here, so we have to be careful about that. So you have A, B, D, then we have the, and this is among everything, right? Because we haven't gone anywhere. So in step 1, we would go to A, right? And why do we go to A? Because it's the shortest path, and most importantly, right, that we don't we didn't have any distance to add, right? So now we're building up a distance, and we have to consider that as such. And so A to A, we're already there, but the distance is set to 1. If I go A, and here it's either A or U, okay, and that would take us to B, that would be at 5. If I go to C, it's 3. So that's where the distance comes in, right? So that 1 plus 2 is going to give me 3. The C was infinity. That's where the infinity comes in, right? Because, why do we say infinity? Because as it grows in complexity, right, we're not gonna exhaustively go through a path and calculate all possible. That could be that could turn into a tractable problem. Okay, we'll talk a little bit more about that as we get into further explanation. Here, when I look at it now, infinity turns into a number because number one, I can get to C now in one step, and that's from A. And it's interesting to note that I can't get there from any other location. So we know now that infinity is replaced. Okay, it's replaced with 3, right? And if I go to D from A, I would have to go through C, and that would be 6 plus the, oh, it's not from A. Sorry, it would be from U. Okay, and that would be the 9. Okay. Because I'm looking at only a single step there, right? So I'm not looking ahead to the shorter consideration, right? So until I get to C, going to D, you're going to see that D goes down. So this is interesting, right? Because every step I go through, and this speaks to the point of being trapped in a local optima, okay? Being trapped into, this is where the greedy algorithm can take you down the wrong path, okay? If you consider, and the way to envision this is if you're looking at navigation or pathfinding, and you may have a weighted or some type of weights associated, and then be led into somewhere where you're being blocked, okay? Perhaps by roads that can't be traversed, or a mountain, or some type of obstacle where it may seem to have a lower cost. And in this case, this appears to be a potential. This is the path through C is actually the lower cost. Okay, we don't know that yet. Okay, so we don't find that out as we move forward. So we go from A, and here we have to, we have this marked. So we have U is marked, A is marked, and from U and A. So if I go to A, that's already there. And to go to B is going to be from U is 5 as before. If I'm going to go to C, it's 3, the existing distance from 9, and I don't know about going to C. I don't find out until later. That is set at 9, and then the rest are set to infinity, right? Because I can't immediately get there, right? So here, I would, out of this, I would pick C. It's just the next shortest path. And then I make the associated considerations from there. And A, B, and C stands to be the same, right? And in D is changed, right? So then the next logical choice is to take B, because that's the shortest path that has been already went to A I already went to C. So the next lowest, it's 153712, and the other ones are infinity. So I'm going to select B, because it's 5, it's lowest cost, and then I add B to the list, right? So then from here, I have 153, it's always going to stay there. Then I have 7, 8, and 12. So from that point, I go to D. However, it is I'm going through the path through not from U to D, but from U to A to C to D, right? That's the 1, 2, 4, and that's going to give me the 7. That gives me the choice there, and then I would remove that from the list, right? So the next consideration is to work from having added A, B, C, and D, right? And U, of course. And from there, I would look. So A, B, C, 5, 3, D, 7 is already chosen, and then the next lowest is 8, and I also have 11 and 12 are filled in, right? Because I have G and H are now reachable, and those are among my considerations, right? So here, I would pick E, right? It's the next logical one, and then I work from there, and the next lowest happens to be from E. I go to H because it's only one, and then transition, and that goes from infinity to 9. And then I would have G. And you got to consider this is directed, right? So I go from H to G, and that is going to pick it because it's 11, and then finally go to F, which is 12, right? It's the final one there. So I don't have any unmarked vertices. So as you mark and you go through and follow this graph, and you can have a good feel for, I think, okay, it was exactly how Dijkstra would work. So the Dijkstra single source, and here's the algorithm behind that, right? So here I have the procedure, the single source shortest path, and I have the input G, the weighted directed graph, and the V is the source vertex. Output for each vertex, the D, V, and D is the length of the shortest path from U to V. I mark the vertex U. For each unmarked vertex within the set of U, if the edge exists, add the weight to the distance, right? And we've been doing that. So this is kind of an algorithm that goes around the strategy we just talked to. So while there exists an unmarked vertex, a V and unmarked vertex, such as the D of V is minimal, and mark the vertex V for all the edges, such as the X is unmarked, do if the distance is less than V plus the weight, then you would add the weight to the distance and add that in accordingly, right? So how do we calculate the complexity here? 1 and 2 is take omega 1 times 3 to 5, take big O of V time the vertices are arranged in heap in order of the paths from U. Here we update the length of the path of O log V time, and there are V iterations and most E updates, and so the algorithm would be big O E plus V log of V time, right? Huffman codes are used to compress data. Here we will study the greedy algorithm. Here we look this at this as a means of data compression. So a given file is considered as a string of characters. The work involved is involved in compressing and uncompressing, and this would justify the savings. Here in ASCII, all the characters are represented by bit strings of size 7. So if we had 100,000 characters in a file, then we need 700,000 bits, right, to store it as ASCII. Here, an example, the file consists of 6 characters and use the fixed length binary. The whole file will be encoded at 300,000 bits, and using the variable length code, the file can be encoded in 224,000. So the variable length encoding scheme aligns frequent characters, short code words, and infrequent characters, long code words, so in the above variable length code. Here the 1-bit string represents the most frequent character A, and the 4-bit represents the most infrequent character F. Here we can denote the characters C1 through N and denote their frequencies. F1 through N, suppose there's an encoding E in which the bit strings S of length S represents C of J, the length of the file, compressed by using encoding E. Prefixes of an encoding of one character must not be equal to a complete encoding of the other. So 1100 and 11001 are not valid codes because you have a prefix. So this constraint is called the prefix constraint. So the codes in which no code word is also a prefix of some other code word called prefix codes, and shorten the coding could shorten the encoding of the others. So to find encoding that satisfies the prefix constraint and minimizes L, E to F. So here we can drive a graph representation here, right? So the prefix code for file can be represented by a binary tree. Each non-leaf node has 2 children. Here we consider the variable length code of the table above. A tree will correspond to variable length code of the table, and the length of the code for character is equal to the depth of the character for the tree shown. Greedy algorithm for constructing a Huffman code. The algorithm builds the tree corresponding to the optimal code in a bottom-up manner. Here, the algorithm begins with a set of C leaves and performs a sequence of merging operations to create the tree. Here, the C is the set of characters in the alphabet. Here's a breakdown on the algorithm for Huffman coding. Input S, a string of characters, and F, an array of frequencies, and output is T. Set all the characters in the heap according to the frequencies while it's not empty. If H contains 1 character, then assign the root of T to X. And here I go through a process of allocating the node and extract the minimum, assign it to the left and assign it to the right. And here from the association of the frequencies, f of x plus f of y, I would insert the f of z into h, right? And perform that until the heap is not empty, right? So you can get a breakdown on that a little bit here. So in the algorithm, it's basically a reduction of the problem with n characters to a problem of n minus 1. And the new character replaces 2 existing ones. So following through the diagram, suppose C of I and J are 2 characters with minimal frequency. There exists a tree that minimizes the length E and F in which the characters correspond to leaves with the maximal distance from the root. So this is how we get the resulting encoding is the either 0, 1, and every time you go down the path of the tree, you are going to come up with the associated designation, right? So D16 gives you the path of 1, 1, 1 going down the tree, and each tree either has a left child 0 or 1, and that's going to derive the associated encoding here. Complexity algorithm here, building a heap. In step 1, it takes big O time, O of n. The insertions, step 7 and 8, and deletions, step 10 and H, take big O log n time. Here the steps 2 through 10 take big O n log n time, and the overall complexity would be big O n log n. And that fractional knapsack, we'll cover that later. Let me, I'm going to wrap it up here. It's a good stopping point, and I'll provide more details on these algorithms. So I encourage you to take a look at the reading. And again, if you have any questions about it, feel free to reach out to me. Thanks for listening. Take care. Talk to you soon. Okay, bye.